All right, so we're going to take just a minute to go over how to create an equation for a quadratic line of best fit. Okay, so you can already see the data here. Just in case you can't read it, this is time in seconds down at the bottom. And this is height in feet over on the left-hand side. And this is about a baseball that's been thrown up into the air. So it's going up, 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 and it gets to its maximum height, and then it comes down, 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 down. Okay, now a couple of things lead us off to show that this is quadratic. One is the fact that it goes up and comes down. So it's definitely not linear. And it's definitely not exponential, because exponential goes flat on one side or the other when it gets to its asymptote. So really, we're down to only a couple of possibilities. It could be a some type of absolute value, or it could be a quadratic, or obviously it could be a piecewise. It could just be a whole bunch of little pieces. But we're going to avoid that if we can. So from this point, our last possibility is, okay, we say, well, one of those two, either quadratic or absolute value. A quadratic should have about the same slope as we go from set to set. And you'll notice that here this is steep. It's getting a little less steep, a little less steep. So the slope is constantly changing when you go from point to point. And because of that decreasing slope, we're going to say, okay, this is probably a quadratic. So I'm going to go ahead and draw in my quadratic graph. It doesn't have to be perfect, but as long as it looks like a quadratic, something like this. Okay, and then it comes back down, and it looks pretty symmetric. Okay, something like that. Okay, so that fits fairly well. Now, from this point, we want to be able to write an equation, obviously. Now, with quadratics, we have two different forms that we know about. Okay, remember with linear graphs, you had y equals mx plus b. You had y minus y1 equals m times x minus x1. X minus x1. And then you had standard form as well, right? The ax plus by equals c. And recently we learned about finding linear lines of best fit and writing an equation for that. For that, we always use these two. We never use standard form. Now, the reason for that is because in these two equations, each of the variables means something with respect to the graph or with respect to our data, right? Here, A doesn't mean, A and B don't, and C don't really mean anything at all as far as specific values, right? M means something, it's the slope. B means something, it's the intercept. And so when those variables mean a specific thing, then it's easy for us to get that information from the graph or from the table or wherever else. Okay, same thing, these are a point, right? Now with quadratics, the one that you're most familiar with is y equals ax squared plus bx plus c. But unfortunately, that kind of fits into the idea of this standard form here. I have no idea why it's standard if it doesn't really do us any good. That c, of course, is the y-intercept. But the other two aren't really that helpful. A does tell us a little bit about the vertical stretch and whether it's right side up or upside down, but B doesn't really help us at all, and A is quite difficult to get from a set of data. So what we need to do is we need to come up with some other way of doing this, hopefully where the numbers are going to be a little bit easier to deal with. Now, one that you should know that you probably don't remember is y equals a times x minus h squared plus k. Now what this is it's just transformational form, where you've got the subtracting h, which is a shift to the right or left, and you've got the adding k, which is a shift up or down. So what this does is it takes the vertex and it shifts it right or left and up and down, and the new position of the vertex is hk. Now, that leads us into the name of this format, which is the vertex form. And you may not remember it as that, but you probably do recognize it as being kind of a transformational form. So we have the vertex, which is hk. Now, there's also this a in front, which is actually the same thing as this a. It has something to do with that vertical stretching. Okay? But again, that's going to be a little bit more difficult to get. Figuring out exactly what the stretch is here can be quite difficult. So we'll work on that later if we need to. All right, so from here, what we need is we're going to go ahead and find the vertex of our graph, because the vertex is usually quite easy to pick off. Now, it's not this one. If it was this one, then all the points would be perfectly symmetrical on the sides. We know that it should be symmetrical, but they're not, which leads me to believe that the maximum is probably somewhere around here. All right, so that's 1.5, so that's probably about 1.7. I'm going to feel comfortable saying that the x value there is 1.7. And the y value is a little bit above that, so the y value is probably about 47. Now, this is just a guess. It's an estimate, but it's a pretty good one at that. So I'm going to go ahead and say, all right, my vertex equals 1.7, comma 47. Now, what I can do with that is I can go ahead and I can put those values in for h and k. So I'm going to recopy this exactly as it was. So I'm going to go y equals a times h, so x minus h, which was 1.7. And if you want, you can put this in parentheses. If it was a negative number, I would definitely put it in parentheses to make sure that I don't forget about the negative. Squared plus k, and k, of course, is 47. Again, if it were negative, I'd probably put it in the little parentheses there. Since it's positive, it doesn't really matter so much. Okay, so there I've got that. I've got 2 of the 3 variables, right? If I were doing this one up here, I'd only have the y-intercept right now. I'd still having to deal with that a and that b. So not only would I have the a, I'd also have that other variable. 2 variables means 2 equations, and now we don't really want to have to mess with that if we don't have to. So we're going to go ahead and take it from here, and we still need a. Now, I don't know if you remember, but back when we did linear graphs, we would have something like y equals 1/2 x plus b, and we wouldn't know what the y-intercept was. We'd be given a bunch of points, a bunch of data, but we wouldn't know the y-intercept. And so in order to get that, sometimes we would just take a point, and temporarily we would replace it for x and y. Now, remembering that in the end, my equation has to have x and y in it. But if I put a point in for x and y, because that should make the equation work, I can find out what b is. We're going to do a similar thing here with a. We're going to pick a point off of the graph that will help us. Now, that point cannot be the vertex. Okay, so I'm going to write that down to remind you, not the vertex. Now, the reason for that is that you've already got the vertex here, and if you put the vertex back in, it's going to kind of blow up, and a is going to disappear. You're going to multiply it by 0, and you're not going to be able to do anything with it. So we want any point, but not the vertex. So I'm going to choose the easiest point I possibly can, which is going to be this one right here, because that one is about 0, 5, right? That's my y-intercept, which, yeah, that would go in for c there if I really needed it to. But I'm going to go ahead and take that 0, 5, and put it in for x and y. So I'm going to go y, which is 5, equals a times x, which is 0, minus 1.7 squared plus 47. So from there, I can actually work all of this out, because I can go 5 equals a times 0 minus 1.7. So I'll go 0 minus 1.7. And then I'm going to square that number, which is 2.89. So 2.89 plus 47. And so from there, it's easy. I just subtract the 47, and I get negative 42 equals a times 2.89. And then I divide both sides by 2.89. So 42, which needs to be negative, divided by, what was that, 2.89. And that gives me a value of negative 14.5. So a equals negative 14.5, because I divided both sides by 2.89. Okay, so there we go. There's my a. And so I can make my final rewrite of the equation, which is, now I need the y and x back in. So y equals a, which is negative 14.5. times x minus 1.7. Oops, that should not be a 5. It should be a 7 squared plus 47. And this is a pretty good guess for the equation of that line. All right, so there you go. 10 minutes it took me to go over how to do a quadratic line of best fit.